Hi physics, today we're going to talk about springs again and how it relates to simple harmonic motion. So the first thing I want to do is remind you about Hooke's law. We called it F equals kx before, but notice now I've introduced vector symbols so the direction matters. All this negative sign means is that the force and displacement are in opposite directions. And I think you'll agree, if you stretch a spring to the right, the spring's going to pull back to the left. When you let go, it's going to accelerate left. That's because the force is opposite the displacement. Okay, now check this out. In this formula, it's really simple. Force and displacement are proportional. So if you double displacement, so multiply this number by 2, force will be multiplied by 2. Now, since the force is opposite direction as displacement and proportional, that makes spring oscillation simple harmonic motion. Remember, the definition for that was that restoring force was proportional to displacement, which is what we have here. The force is restoring because it's opposite displacement, and we can tell it's proportional because of Hooke's law. I'm going to give you this formula now. This is the period of a mass spring oscillator. Okay, it's really similar to the period of a pendulum, 2 pi, and then under the square root we have the mass at the end of the spring, and k is the spring constant. I've set up a really short example here. Okay, so I got a 10-gram mass attached to a spring with a small value k. We're just going to use our new formula here. So make sure your mass is in kilograms. So it's actually going to be 0.01. Oops. Divide by 0.2. Square root multiplied by 2 pi. Just push the right buttons and you'll be good. Okay, so here I've got a period of 1.4 seconds. All right, I'm also asking us to get frequency here. Nothing's changed. You know how to find frequency. It's 1 over period. So I get 0.71. Units there are going to be hertz. Looks good.